So I'm going to talk about intuition busters. This is a topic that I really love. It's, the goal basically is to pick some interesting problems that are unintuitive, at least to me and some other people. And so by presenting them, I want to improve your intuition. Hopefully you'll learn a few things to think out of the box and also have some fun. So this is going to be sort of quick slides.
You've been muted. To unmute yourself, press
be a fun one.
*6.
Okay,
you are no longer muted.
A few things about this talk. So there's some facts that I'll share. Again, I think they're unintuitive. Several of the issues are sort of teasers or problems for the audience to sort of think about. If you're familiar with it, don't just say, oh, it's FUBAR. Give others a chance to listen. And then, I'll share it out, give you a few seconds to think about it, maybe 30 seconds to a minute.
This meeting is no longer being recorded.
And then we'll get to the answer. And then if you got quick questions in the middle, feel free to ask. If they're going to be long, philosophical, please push it to the end. I can stay a few minutes afterwards and answer all those. Okay, so let me start with a sort of a warm-up thing that is kind of an interesting, unintuitive thing. And it's the dwarf planet Pluto. So this was discovered back in the 1930s. And then it was named a few months later. And this was interesting because today we think of as crowdsourcing as something that we only do in the modern world. But it was actually a crowdsourcing exercise. They asked people to submit names for this new planet. And this 11-year-old schoolgirl won. And the name comes from the god of the underworld in mythology. And then Walt Disney, apparently named the dog to, capitalize on the newly discovered planet. And then in 1992, they said, oh my God, we're discovering all these asteroids or bodies in the Kuiper Belt. And then they said, what are we going to do? Oops. Okay. You probably made me an attendee, right? Manage content, maybe? No. I don't see the orange box. Is it ready, or do you want me to continue or not? Okay. I'll continue. Hopefully, the guys on the phone, you'll get the slides showing in a few minutes. And then so in 2006, look at this, delta basically from all the new bodies. They basically redefined the planet so that the definition for a planet so that Pluto doesn't meet it. And, in 2006, the American Dialect Society voted Pluto as the word of the year, and it means to denote or devalue. That's all these things are happening. And question for the audience, how many times did Pluto circle the sun since it was discovered? So again, just think for yourself. How many times did Pluto circle the sun since it was discovered? I think we're going to get the slides to show up in a few seconds. There's an orange box around it. Cool. Thank you. So it's about a third of an orbit. So it takes Pluto 248 years to circle the sun. And throughout all this time, it's gone sort of about a third of the way. Okay, fishing rod. So this guy brings a 5-foot-long fishing rod and wants to get on the bus home. And the driver says, sorry, nobody's allowed to bring anything longer than 4 feet on the bus. The man goes out, goes to the store, and then is able to catch the next bus, still carrying the same rod, but the driver says nothing. Question is why? Exactly. Nice. So all you got to do is buy a 3x4 box and put it diagonally. Okay, and then think about this when you go to airlines and they measure you. But it's interesting that if you think about this, and we're mathematicians and data scientists, we want to push this to the extreme. You can actually bring a 6.9-foot rod if you get the 4x4x4. Okay, next one. So this is sort of a simple exercise. I'll ask you to do this. Again, think about your intuition. What comes to your mind first? So try to do this quickly. I'll show you 2 statements. One is on the left, one is on the right. And I'll ask you to raise either your left hand or your right hand, matching to which one of the statements refers to a larger number. Okay? Ready? Okay, so this is not too hard, right? Hopefully most of you raise your left hand. But we're going to go through another exercise, a little bit harder. Ready, set, go. Some right, some left. Okay, so left is the right answer. And the reason is every word on the right is a strict letter on the left. Right? It's just a strict subset. Yet, the reason we get this wrong so much, there's a few people in the room that sort of voted one way and the other, is because of what's called in psychology the availability bias. It's very easy for us to think of a lot of words that end in ing. But this one, sort of 6-letter words that have N as the 5th letter, is sort of harder to parse for us. And even though it's a subset of this, several people thought that this is bigger because of this classical availability bias. Okay, this is something interesting called the Banzhaf Power Index. It comes from this fun book, Mathematician Reads the Newspaper. If you have 3 stockholders, and they own 47%, 49%, 44%, and 9%, and if you need 51% to pass the measure, then even though the third guy drives a Yugo, they have all equal power. Right? You just need the third guy all the time. Now think of the opposite, which is you got these 4 people holding these holdings, and you never need the last guy. Right? Just ignore him. Never tips the scale for the other guys. And there's another example which is a little more extreme. The first 3 here all have equal power. This guy is a dummy. Okay. So anyway, there's something called the Banzhaf Power Index, which is the number of ways you can change a coalition. Okay, so actually somebody worked on that, and you can drive up this formula. And why is this sort of interesting? It's interesting because of the Supreme Court. So there's 9 judges, and they all have equal power. But if you think about it, if there's a subgroup of those 9 that says, you know what, we're going to get together, 5 of us, before the big meeting, and we're going to make the decision between the 5 of us. And then once we decide, we're all going to agree. So they have a majority, right? And now the Supreme Court is basically ruled by 5 judges who have a pre-meeting, and they make the call, right? This is a little disturbing, but it gets worse. What happens if 3 out of the 5 decide to do a pre-meeting to the pre-meeting and make the call? Right? So these 3 decide, and then it forces the 5, and the 5 force the 9. Right? So kind of concerning these days. Okay. Just a few things about linear measures and volumes. We often tend to sort of not appreciate linear numbers and volumes. So I got a couple of examples that are really fun. So if you take nickels and stretch them from sea level to Mount Everest, okay, it takes about 4 million coins. And the question is, how large a box do you need to put these in? So you only need 6 feet to decide. Okay, now take the interesting question of the Grand Canyon. So if you take all living humans and put them end to end, they go basically to the moon and back 8 times. So this is linear. Seems like a big number. But now if you try to fit every human being into the Grand Canyon, and you give each one a house, which is a cube, which is n feet by n feet by n feet, how big would n be? Right? And it's about 20 feet, so you get more than your office. Again, so our intuition about volumes is really, really poor. And like most people think, they're crouched together and it's going to be really tough, but it's fairly comfortable. Cigarette smoking. Cigarette smoking kills 480,000 Americans every year. Right? And the problem is we don't have sort of intuition about how big this number is. So one way to make that more interesting is to equate this to 747 jumbo jets crashing. This is the equivalent to 743 fully loaded 747 crashing every day of the year. Right? That makes it a lot more sort of, when there's a plane crash, it's all in the papers and everybody talks about this and we do all these investigations. But hey, this is what cigarette smoking does. So very, very interesting way to sort of turn a number into something that resonates a lot better. Okay, so here's a nice riddle for you. So each card has a letter on one side and a number on the other side. Now, I want you to think for yourself, don't yell it out, think for a few seconds about which cards you need to turn over in order to test the following rule. And the rule is if there is a vowel on one side, there is an even number on the other side. Okay, so I'll give you 30 seconds to think about it. Okay, so most people get A. What's the second card? Yeah. So 2 is incorrect because it doesn't say anything about what happens if in the other direction. And the rule is that actually less than 20% of the population get A and 7. And the reason for that is if A implies B, it's the not B that implies not A that we have to think about. Okay, priors. I'm going to show you a graphic image, and don't worry about it. It's not as disturbing as it looks, but it's just our way of interpreting things. Our brain is used to seeing some things, and when I do something that's a little abnormal, then it looks a little scary. It's my son, by the way. So there's nothing wrong with him. It's just a pacifier. But it's just like very, very scary when you first look at this. It's all about priors. We have our priors. Our brains tend to interpret things one way. And when you do something that's sort of unexpected, it's hard for us to see it until, in this case, I'm helping you see it. Okay, a few things about velocity. So this is, basic math. If you drive 60 miles an hour, it takes you 60 seconds to travel a mile. At 120 miles per hour, it takes you 30 seconds to travel a mile. So at what speed would it take 45 seconds? Right, so again, this is sort of, when we talk about fractions, our brain doesn't seem to work very well. So the answer is 80. And it's all about, distance over time. And our intuition sort of tends to fail in these cases when you have a ratio. Okay, here's another example of an interesting challenge. So we have a driver who finishes half his racing track at an average speed of 150 miles an hour. Right? He drives fast. At what speed does he need to drive the other half to average 300 miles an hour? Yep. So it's impossible for him. And, the basic point is that, if X is the length of the track and you need to finish it at 300 miles an hour, then this is the time that you have, but you already spent all the time. Right? So you have 0 time to finish the other half of the track. And, just to make sure people understand, if he drives 450, which is sort of the simple, if you don't think about an answer, then the average will be 225. Okay, so I'll do a little bit of statistics. I just want to make sure everybody understands the terms. Hopefully everybody in the room does. So, if I take a series of numbers, then the mean is just the arithmetic mean. You add up the numbers, you divide by n. So for this series, it's 100. There's sort of other means like geometric, harmonic. The mode is the value that occurs the most frequently. In this example, it's 5. Right? Occurs 3 times basically above. And then the median is sort of the middle value of the distribution. By most definitions, it doesn't have to exist in the series. So 7.5 is what you'd say is the median. again, when it's an even number, then you have to sort of, the convention is to average the two. Usually the statistical definition is, says any number between 5 and 10 would actually be the median. And then, you know, you're familiar probably with the normal curve. It's a Gaussian distribution. The mode and the mean are the same for a Gaussian distribution. And then, you know, 68% fall within 1 standard deviation, 95% fall within 2 standard deviations. This is what, you know, the rule of thumb, though, this is 1.96, but everybody's familiar with this thing. Now, a few things. Most value can be lower than the mean. Right? So 75% of the values in the above example are lower than the mean. It is possible that when George Bush went from DC to Texas, the average IQ rose in both states. Right? This is not something obvious, but it is possible that, you know, you're lower than the average here. Therefore, when you move to the other state and you're average than the average in this new state, you're raising the averages in both. Let's talk about this thing, which is sort of a very, you know, everybody likes to talk about money. So let's assume that you take $100,000 in some volatile stock. And what I mean by volatile, each year it either goes up by 60% or it falls by 40%. Right? And the question is, well, okay, so now you're going to invest for 100 years. And your heirs are going to get the money. And the question is, what is the expected value of the stock after 100 years with such probabilities? And then what is the median? And what is the mode? Okay, so our intuition is not good at 100 years, but what's interesting here is that these values take off very, very different numbers. So the expected value is $1.4 billion. Okay, so you basically say it's either 1.6 or 0.6, and you raise that to the power of 100, and it becomes this really, really large number. And you're going to say, wow, my children are going to really, really love me. But the problem is, the mode and the median are $13,000. That means that half the people will have less than $13,000 after investing 100 years in this volatile stock. Right? So pretty shocking, pretty amazing. And, you know, I ran some simulations just for the fun of it. And you can see that, you know, this is a typical distribution. This is another typical distribution. You get this one event that gives you an amazingly large number, and then everybody else averages out. You know, the mode turns out to be 12,989. Here's another run that I did. You know, you get a very large number, but the mode turns out to be same 12,989, the median and the mode. So pretty scary. But you know, this is compound interest. It's really good if things go up. But you know, if things are volatile, you can hurt really, really badly. So this is sort of an interesting way to think about the impact. If you think about long-term stock investment, they earn about 6.8%, and this has been measured over a very long time. Yep. Correct.
And so one of the places where humans have problems is understanding what a 50% gain means, and that it's not the same as coming back from the point.
Correct. And the point is, this is, if you think about it, this is 1.6 times 0.6, which becomes 0.96, right? And this is why we choose this example, because the product is sort of lower. That's what you need for computing the median. And the average is what you need for computing the mean. And so they're right on the border of one, and one turns out to be, you know, diminishing over time, and the other one turns to be increasing over time. Okay, so yeah, so over long years, over many, many years, the stock has, you know, been rising. The market's been rising at 6.8%. And so think about this interesting problem. According to Wikipedia, Manhattan real estate, one of the most expensive in the world, is worth about $3 trillion. It's the latest number that I could find. Now, it's often says that the Native American who sold Manhattan in 1626 for $1,000 were rooked by white men. But if the Indians were just to invest this at 6% annual, they could actually buy Manhattan today with all the improvements that were done to it. Yeah. Is what? It's dollars and dollars, right? If they took the, I mean, they sold it for $1,000, they invested, they would be able to buy Manhattan today. Right? So it is a fair comparison. And inflation, by the way, is nowhere near the 6%. So you are going to make a lot of money. So all I'm asking you guys, invest in your 401ks. Well, remember, Okay. Probably most of you are familiar with it, but I'll just mention it for those that are not. So the probability that a random person has a birthday on some random date is 1 over 365, or 0.274%. And the question is, how many people do you need to have in a room so that the probability is over 50% that 2 people share a birthday? Right? So it turns out to be 23. Somewhat unintuitive. And, so if we have 42 people in a room, the probabilities starts to get really, really high. And, the reason for this is basically that for every person that you add, they can't have another person that have the same birthday. So when you look at the probability, it basically goes like this. This is one way of doing it. The other one is doing this series where each time you're saying, well, I can't have these 362 days, or I can't have these 361 days, etc. Okay, here's another problem. You got 3 prisoners, A, B, and C. They're all in separate cells, and they're sentenced to death. Right? We all in math love these, prisoners and death and stuff like that. Let's see how many problems we have. So the governor selects one of them at random to be pardoned, and then the other 2 will be killed. And the warden knows which one is going to be pardoned. And so one of the prisoners starts to beg and say, can you tell me which of the other 2 people is going to be executed? Okay, so you're not asking about yourself. You're asking which of the other 2 people is going to get executed. And so the warden sort of after a while says, okay, fine, B is going to be executed. And now the question is, has the person gained information? Right? And it turns out, the prisoner may think he's, pleased because now he's basically used to have a survival rate of 1/3, right? One of the 3 is getting pardoned. And now there's only 2 people that are left, A and C. And so he concludes that, wow, I've just gained information. My chances are gone to a half. But he's wrong. In fact, if anything, when he tells this to C, C celebrates because his probability of living just went up from 1/3 to 2/3. And so this, by the way, many of you are probably familiar with the Monty Hall paradox. This is exactly the same, although I like this wording because people then don't know the problem. But just for those of you that haven't heard it, and for the easy explanation, I'll tell you the Monty Hall. You're in a game show. You're given 3 doors. Behind one of the doors is a car. Behind the 2 other doors, there's goats. You pick a door, say door number 1. You don't know what's behind it. And the host, who knows what's behind the doors, opens another door, say door number 3, says, see, there's a goat here, and then asks you, do you want to switch or do you want to stay? And so the intuition says, doesn't matter. I picked the door. There's another door. But it turns out, if you just go through the 3 possibilities, it's pretty obvious that you should switch. So think about this. There's a door here. You picked number 1, and the 2 goats are over there. So the host can either open door 1 or door 2, but you're going to lose in all cases if you switch. But let's take the same example, and there's a car. The host has to open door number 3. So if you switch, you're going to win. And then in the 3rd case, again, the car is here. The host must open door number 2, and then so you're going to win. So in 2 out of the 3 cases, you're going to win if you switch. Right? And of course, by symmetry, whichever door you pick, the same argument holds. So kind of an interesting example of, yes, this actually gives you additional information, and you should switch. Let me take a Bayes rule example. It happens a lot in medicine. So you've taken a test for some dreaded disease, call it D, and that test is 99% accurate. What do I mean by that? If you have the disease D, the test will be positive 99% of the time. If you don't have the disease D, the test will be negative 99% of the time. But D is relatively rare, and only 0.1% of the population has the disease D. And so you go to the doctor, you take the test, and it comes out positive. The question is, how concerned should you be? Right? There's a 99% accurate test you just ran. It tells you you got the disease. Turns out you shouldn't be worried too much. You only have a 9% chance of actually having the disease. Right? And so here's the sort of intuition that helps understand this. If there's a population of 100,000 people and 0.1% of them have the disease, then 100 people have the disease. Now, 99 of this 100 people will test positive. The problem is this thing, right? 1% of this number, or 99,900, will also test positive. So it's going to be 999 healthy people that will test positive. And so the probability of D is therefore these 99 over the sum, which is 9%. And if you like Bayes' rule, this is the Bayes' rule formulation. Unsurprisingly, you'll get the same number. Right? So our intuition is often wrong about things that are rare. And very, very important when you make medical decisions to actually understand what's called the base rate. You know, what is the probability of this thing in the overall population? Because that has a massive impact on the result that you get. Here's a few examples from How to Lie with Statistics, a really fun book, really old book. So here's a statement. U.S. Steel showed the average weekly salary increased 107% between 1940 and 1948. The only thing they forgot to mention is that they had a lot more half-time employees. So yeah, if you work full-time, your salary doubles. Here's one that was used by the Army. So the death rate in Navy during the Spanish-American War was 9 per 1,000. The civilians in New York during the same period, the death rate was 16 per 1,000. So the recruiters tried to convince people that it's safer to go into the Army. Right? And of course, the problem is the groups are not comparable, right? If you go into the Navy, young people, they're known to be in good health. And the civilian population includes a lot of infant mortality, old people, ill people. This is an example that highlights the support problem. If you get a probability number, you always have to check how much is it based on, or how many people is it based on. So here's one study that shared that 33% of women at Hopkins married a faculty member. Okay, and as you can guess, there are 3 women, one of them married a faculty member. So yeah, so we have to be really, really careful. A lot of our algorithms, especially if those of you that are aware of something called the bias variance trade-off, they start to fail when the populations start to get small, because you get into these spurious statistics and overfitting. And that's why you need to sort of smooth some of the probabilities and say, okay, I don't have enough support here to estimate the probability. I'm going to intentionally create a skew towards some hierarchical parent of mine, and I'll bias it that way. Survivorship bias. Very, very common problem, but it's an amazing story. So in World War II, there was a decision to fund. There's a lot of planes going down, obviously, and somebody said, we're going to fund adding armor to bombers. Okay, so the natural inclination was they went and recorded where the planes were getting hit the most. It's like the wings, the tail gunner, the center of the body. And they said, okay, where they're getting hit the most, we should add armor. And then, to the data scientist's pleasure, some guy there was actually a little bit more aware of the math around this. And Abe Wall pointed out that these were the worst places to add armor. Okay, so where you see all the bullets hitting, don't protect those places. Go the other way. Why? Because the bullet holes are uniformly distributed. Somebody shoots down, and there's a lot of holes on the plane. You should add the armor where there are no bullet holes. And why is that? because it's those planes that never made it back. Right? So somebody that gets hit in the cockpit, the plane ain't coming back. And so we often forget this, right? I shared with you the example. It looks reasonable. You mark the planes, you instrument things, and then you look at, where the problem is. But you forget that you've lost certain planes in your instrumentation, and those are the ones that you really care about. And so this is sort of the opposite conclusion of what you expect. Very, very important lesson here. And this happens all the time. So there's a famous book called In Search of Excellence. One of the best business books in the 1980s. Best-selling book, 3 million copies sold in the first 4 years. What it did was it shared the practices of the excellent companies. The best companies out there, they went, Kinsey, I believe, and they studied them. But then you look at this, and people, a couple of years later are like, wow, we're looking at these excellent companies, and they did really badly. Like, they actually did worse than the S&P 500. Okay? And so the problem is you just can't take the successful companies. And I think this is one of the best examples that I've seen of sort of making sense of this. So let's say you can do something on this line, right, which is sort of a risky business practice. Okay? So if you do this, a little bit of this practice, things are going to move a little bit. But you do more and more of this business practice, and you're either going to be very successful or you're going to do really, really bad. Okay, and the more you do it, obviously the more it starts to vary. You're either very, very successful or you're really, really bad. Now, if all you do is study the successful companies, what you see is this. Right? These guys went bankrupt. They don't exist. And now you see this business practice. And the more you do of this business practice, it looks to you that the more successful you're going to be. Right? Terrible, terrible way to study business. Yet the book is, of course, the guy is very, very rich. There's lots of stories about how they did this. There's a lot of flaws in how they did the studies. But I think this key point about survivalship bias is really, really important to understand, because you're going to actually arrive at the wrong conclusion about what to do for the business. There's another great book called The Halo Effect. And the halo effect basically means that when you rate somebody on several axes, you're going to correlate too many things, right? If there's supposed to be these independent axes, it actually comes. The halo effect was turned by a military study where some guy noted that when the soldiers were rated, those that were good on everything. They could shoot better, they could run faster, they could do things better. It turns out that it wasn't the case. It was just the bias of the people rating. If somebody's good, you tend to rate them good on a lot of attributes, even though they're supposed to be more independent. But so here's a really good example that probably impacts us a lot. So a nice study that took participants, and they were asked to estimate future sales based on financial data that they gave. So you took a bunch of groups, you gave them, the 10K report from the company. You say, what's going to happen to them in the next year? What will they report? And the data was intentionally, it was a real company, but the data was a little fuzzy. It was hard to make the predictions. And what they did is at the end of the study, they told half the groups that they performed really well in the top 20%, and they told the other random half that they performed really, really poorly in the bottom 20%. Now you ask the random groups, what did they think about the way they operated? Okay, so those groups that told to perform well rated themselves as highly cohesive, better communication, open to change, superior motivation, and the low performance, really, really bad on all of these. Right? And so these attributes are important, but you can never hope to measure them by asking people when they know the outcome. Right? So you think about it this way. There's a group that's very passionate. They keep arguing. And then you tell them they performed well. What did they say to themselves? We were honest. We didn't hold back. We had a good process. That's why we did so well. And if they performed poorly, they say, well, we argued and fought. We were dysfunctional. Next time we'll be respectful and disciplined. Now what happens to these groups? They actually were polite and respectful to each other. You told them they did well. They say, wow, we were courteous, cooperative. We respected each other. We didn't fight. We had a good process. This is why we did well. And then, of course, if they performed badly, what did they say? God damn it, we were too polite. We censors. Next time we should be more direct, open, less concerned about other people's feelings. These books that you see, like In Search of Excellence, all their data comes from these interviews that they do with the companies. If you're in a successful company, they're highly biased by looking back at what they did and saying, we were successful because of whatever. Right? But these are very, very, very biased interviews. So, here are basically 3 books that the halo effect basically ridicules to say, not very, very good. They're all based on these interviews. The latest one, which is Good to Great, again, one of the best-selling books of all time. It's still #1 on Amazon when I looked at it. Company and Business Practice. By the way, the prices are not that great. This is $4, $2.99. This is a cent now. I mean, you read the book and it looks great. I mean, Collins picks 11 companies, tells you how he picked them scientifically out of a whole bunch of 1,435 companies. But, a few years go by, and out of the 11, he picked 2 that went bankrupt. Not a good success story. It's pretty actually hard to pick 2 companies that go bankrupt a few years later. And the reason is it's all, it's basically all backwards looking. Companies that did well aren't going to do well forward, especially based on interviews. And, he talks about how they interviewed companies, all these companies, and had reams and reams of papers. And, at the time, I think it was megabytes of data. It was kind of funny when I went back and looked at that. They were proud that they had, megabytes of data. Yes. Don't listen to science. Everything you do, just fake it, write a good story, and everybody will love it, right? Yeah, I mean, that is a problem. These guys really know how to sell, how to tell a story. The stories are wonderful. Yeah.
An interesting thing, I can't remember if it's Good to Great or one of the other ones. They actually attempted to compare the company.
Yes, it's Good to Great.
So
yeah.
It seemed like they were trying to do that.
Correct. Yeah, so the reason, okay, so the question is, I'm getting flagged by the back. So in Good to Great, they picked 11 companies, and then they picked other companies in the same industry that didn't do well. And they were trying to see the difference between them. So this is actually, from a methodology standpoint, a lot better. The key point about the halo effect book is that a lot of their decision was based on interviews. And if you take a successful company and you say, what did you do? Everybody's going to tell you glorified things about they did. It's the 20% time that made us successful at Google, right? It takes a while to realize that maybe it's not that it. So the halo effect is basically one of the explanations for you can't pick these things after when you interview people, you can't take the successful one and ask them what they did and the unsuccessful ones what they did, because they're all going to be tainted by the actual performance over the last few years. That's sort of the main lesson that he makes in the halo effect. So expectation bias. This is something that we all fall into. Very, very important for us to realize that when you get the result you want, you stop. If the result is off, you go back and check your math, and you find the flaw, and you fix it. Okay, so let's look at a few examples. So there's an experiment, a very famous experiment, to basically measure pressure due to light. And this is the quantization of light, so they're expecting to get results that are, basing the theory. And this very famous article by Nichols and Hull, and, they basically show, wow, we got this, we ran the experiment 1% off from Maxwell's theory. So they publish. Paper's very, very famous. So famous that people go and say, wow, let's repeat what they did. And so a couple of people went down, reanalyzed their data from their logs, and they see, oh my God, they use an incorrect value for the mechanical equivalent of heat. They took the logs base 10 instead of base E. Right? And there's all these other things. And they get to within 1%. And so if you do everything correct, you're off by 10%, which is cool. But as soon as these guys got to within 1%, they're like, whoa, cool, let's publish. Right? But in reality, if they were 30% off, they would go and find these errors and correct them to get a little closer. We do that all the time, I think. Okay, so here's another example, which is you do a result, you publish a result, and the example here is pretty amazing. Speed of light. What could be more fundamental in physics? Right? So you look at the results, this guy publishes, here's the number, here's my error bar. Next guy comes along, says, does the math. I'm very close to this guy. Cool. This guy's a little worried, but hey, the confidence intervals overlap. I'm okay. More and more people publish. But it turns out all of these guys, their error bars are off from what we know today and we believe is a real number. These have really, really small error bars. Right? So what happens? Like all these guys are off and misestimating. And it's basically this idea that they do the math, they get a number that overlaps with the previous publication, and they publish. But if they were to work on it a little bit more, they might find that this is a mistake. Now, what does this cause, by the way? So all these publications happen, and then some people start to report higher numbers, right? I don't know if I have it on the slide, but in reality, what happened is proposals were starting to come out that the speed of light was accelerating. So there's a guy around, the late 40s that basically said, there's something wrong here, speed of light's accelerating. There's another guy that says, these guys went bad on their math, and he publishes a result that sort of, seems to unify all of them. He says the error bars are off. And his result lasted for like 7 years or 9 years, I think, before we were more than 2 standard deviations off from that result. Okay, this is, close to my world of running experiments. When you run controlled experiments, we often use the null hypothesis statistical testing. Really, really standard common methodology. You get this in our scorecards. And the standard rule says if your p-value is less than 0.05, you should reject the null. Okay, everybody's familiar with it. Okay, so here's some misinterpretation. So all of the following are incorrect statements. If p is equal to 0.5, then the null hypothesis is only a 5% chance of being true. If you see p greater than 0.05, there is no difference between the groups. If p is equal to 0.05, then your observed data would occur only 5% of the time under the null hypothesis. And if p is equal to 0.05, it means that if you reject the null, the probability of a type 1 error or a false positive is only 5%. Those of you in the audience, read each of those statements. All of them are incorrect. And yet we all fall into this trap of implying that one of these things happen. And the most common problem is that p-value is the probability that the value that you see is more extreme. Sorry, that x, the true value, is more extreme than the value that you see, conditioned on the null. Okay? What we really want is the opposite. We want to see what's the probability that the null is true given that we've seen some piece of data. And so you will have to multiply by sort of the background rate of success, something that we don't often know. And therefore, it's easy just to assume that that doesn't change the result. But it does. And you should all be aware that if you're trying to find something rare, then the p-value that you're using has to be a lot lower, at least a lot lower than the rate at which you're looking for success in that domain that you're working on. Simpson's paradox. This is one of those things that is not just theoretical. And how many people know about Simpson's paradox? Just raise your hand. Okay, so just about a third, maybe a quarter. I think it's one of the more interesting things that I've made mistakes in life about. So I want to make sure everybody's aware of it. It really happens. I'll share with you examples. They're all going to, for those of you that are not familiar with it, they're all going to seem like they're impossible. And then I'll explain to you why they happen. So drug treatment. So it's a real example. You got 2 treatments for kidney stones. A succeeds at 78%. B succeeds at 83%. So B is better. Okay. Now somebody comes along and they do the analysis and they split by stone size. And there's only 2 possible values. Either you have small or large. There's no like third alternative. They pick a threshold. If you're less than the threshold, you're small. And so they look at the data for small kidney stones, and A is better, 93%. Treatment B is 87%. And then they do the same for large stones, and A is 73%, and B is 69%. So if you have small kidney stones, you should do A. If you have large kidney stones, you should get treated with A. Yet if you look at the overall result, you should do B. Now, you either have small or large. You have one of these 2. Okay, next example. Again, there's a court case on this, and there's a guy from Berkeley that was involved, a stats professor. So somebody goes to Berkeley, gets the data, and they claim that women are sexually discriminated. Only 34% of women are accepted, and then 44% of men are accepted. So head of school goes, let me find that department that screws things up for me, calls all the department heads, says, I want the statistics from each of you about your acceptance rate for males and females. And what do they discover? All departments accept more women than men on a percentage-wise basis. Every department actually is biased in favor of women. Yet when you look at the university, they favor men. There is nothing inconsistent about these two statements. It is possible, and it happens. Actually happens so much that people sued about it. Okay, third example. This happened to me. I worked at a company called Blue Martini. We saw this statement: multi-channel customers spend 72% more per year than single-channel customers. Right? If you shop at stores online and in some of their channels, this is what they said. And we plotted this. We plotted this result, and we saw, my God, if you're purchasing once, not true. If you're purchasing twice, not true. If you're purchasing 3 times, not true. So again, I remember we were like looking for the bug for a very long time, and we realized there's nothing wrong with these statements working out together. When you aggregate the data from the purchases, you can get the above rule to be true. I'll do a final example from baseball. Batting average is basically the percentage of hits. You can hit higher batting average than another player during the first half of the year. You can do the same thing in the second half of the year. And yet when you aggregate the 2 halves of the year, you will be a worse player. Okay? And just to convince you, here, I'll leave this on the board for a few seconds. Here is the actual example. So in the first half of the year, you bet you do 0.4 versus 0.35, 350. This one you do 250 versus 200. So you're better in the first half. You're better in the second half. Yet if you add up the season, you're losing. Okay, this is sort of a pretty convincing argument with the actual numbers that this can happen. So we all get confused by these percentages and probabilities. And so it happens a lot. I want you to think about it. When you are running an uncontrolled experiment, you can have these confounders. And you have to think about, is it possible that I have segments that cause this reversal? And last week we were at a big meeting and we saw this. It was like females do more searches than males, but if you split them out by country, almost every country has the other sort of reversal thing. And this is an example where you can see if there's only 2 countries in the world. I can do the same example as before. It's possible that in the US, males search more than females. In India, males search more than females. When you add them up, you get a reversal. Happens in controlled experiments. When you ramp up experiments, you can have an experiment that wins on Friday, wins on Saturday, but is going to lose overall. This is why we don't allow you in our system to ramp up and add the results, because you're exposed to Simpson's paradox. When you change the probabilities that you're running an experiment, you have to reset. Okay, I'm going to end with one fun example. Comes from Angels on the Pin. Just a fun example of how to think outside the box. So the question is, can you determine the height of city center, pick a random building of your choice, with the aid of a barometer? Okay, and here are the best answers that were found. Okay, the first one is you take the barometer to the top, you attach a long rope, you lower the barometer to the street, then you measure the rope length. Second best example, you drop the barometer from the top, you time how long it takes to drop with a stopwatch, and then the height is a simple formula, right? Distance equals half AT squared. Third example, you take the barometer on a sunny day, you measure the height of the barometer and the length of the shadow of the building, and then using simple proportions, triangle, you determine the height of the building. You take the barometer, begin to walk up the stairs. As you climb up the stairs, you mark the length of the barometer along the wall. You then count the number of marks, and this will give you the height of the building in barometer units. And then the answer for all of you guys in marketing or other examples, you go to someone in facilities, you say, I have this fine barometer. If you tell me the height of the building, I will give you the barometer. Thank you very much.